Alright, let's go. Number 10. Greater Adria. A continent the size of Greenland was pushed entirely into the Earth's mantle, and its remains now physically compose the Alps, the Apennines, and the Balkan ranges. The collision happened at roughly 4 centimeters per year. That sounds slow. It isn't. Over 30 million years, that rate drove an entire continental plate, Greater Adria, roughly the size of Greenland, beneath the Eurasian plate. The overlying crust buckled upward, and the sedimentary layers that had accumulated on Greater Adria's surface for hundreds of millions of years were scraped off, folded, compressed, and thrust skyward. Those scraped remnants now form the limestone peaks of the Dolomites, the structural core of the Apennines, and significant portions of the Balkan mountain chains. The continent itself did not survive the process. It was subducted, pulled down into the mantle, where it continues to exist not as a landmass, but as a seismically detectable anomaly at depths exceeding 1,500 kilometers. Geologists at Utrecht University reconstructed this event in 2019 using plate tectonic reconstruction, combined with paleomagnetic data from rock samples across southern Europe. The data revealed that Greater Adria had existed as an independent continental block for over 200 million years before the collision began. It was surrounded by shallow tropical seas on its northern and eastern margins. Its sedimentary record, preserved in the rock layers now elevated into mountain ranges, contains fossils of marine organisms from the Mesozoic era, evidence that this landmass spent most of its existence partially submerged, accumulating thick carbonate deposits on its edges while its interior remained above sea level. The subduction did not happen uniformly across the plate. Some sections of Greater Adria's crust were forced down at steep angles, while others sheared off laterally, leaving fragments embedded in the overriding Eurasian plate. These fragments, called terranes, are geologically distinct from the surrounding rock. Their magnetic signatures, mineral compositions, and fossil records do not match the European mainland. They match each other. They match a single lost plate that no longer appears on any map. The mechanism is straightforward in principle but brutal in scale. When two continental plates converge, neither is dense enough to be fully absorbed into the mantle. Oceanic crust, which is denser, subducts readily. Continental crust resists, but Greater Adria was partially oceanic at its margins, and the geometry of the collision allowed the Eurasian plate to override it almost completely. The top layers were stripped like skin from a fruit. The rest descended into the mantle below. Deep seismic tomography, the imaging of Earth's interior using earthquake waves, has since confirmed the presence of a cold, rigid mass beneath the Mediterranean region, consistent with subducted continental lithosphere. Its dimensions roughly match the estimated size of Greater Adria before collision. The mass is still there. It is still cooling. It is still distinct from the surrounding mantle material. The mountain ranges built from this event are not static. They continue to rise. The collision that consumed Greater Adria has not fully stopped. The African plate still pushes northward into Eurasia at roughly the same rate. The Alps gain altitude at approximately 1 millimeter per year. Earthquakes across Italy, Greece, and the Western Balkans are residual evidence of a process that began over 100 million years ago and has not yet reached equilibrium. The system remains active. The remains of Greater Adria are visible from space. They just aren't recognized as a single entity. They are mapped as separate ranges in separate countries, studied by separate institutions. But the rock tells a different story, and the body of that continent has not finished sinking. Number 9. Zealandia. 94% of an entire continent sits below the Pacific, and it wasn't formally classified as one until 2017. If you're not subscribed yet, now's the time. This list only gets heavier from here. The first satellite gravity maps in the 1990s showed something anomalous across a vast region of the Southwest Pacific, a continuous, elevated block of continental crust stretching from New Zealand northward to New Caledonia and westward toward the Lord Howe Rise. The structure covered approximately 4.9 million square kilometers, larger than the Indian subcontinent, but 94% of it sat beneath the ocean surface. No one called it a continent. The definition itself was the problem. Continental status required elevation above sea level, a distinct geological foundation, a thick crust, and clear boundaries from other plates. Zealandia met every criterion except the first, and that one was arbitrary. 2017, a team of geologists led by Nick Mortimer of GNS Science published a paper arguing that Zealandia satisfied all four conditions and should be reclassified. The case was built on decades of rock sampling, dredge surveys, and seismic profiling. The crust beneath Zealandia ranged from 20 to 40 kilometers thick, consistent with continental crust, not the 5 to 10 kilometer thickness typical of oceanic basins. The rock types matched: granite, schist, greywacke. Not basalt. The boundaries were sharp. Zealandia was not a diffuse extension of the Australian plate. It was a discrete entity, separated by clear tectonic margins. The submersion happened gradually. Around 80 million years ago, Zealandia broke away from Gondwana as the Tasman Sea opened. The crust thinned as it stretched. Unlike Australia, which retained a thick, buoyant core, Zealandia's crust was narrow and elongated, with no single mass dense enough to resist the pull. As it moved away from the spreading center, it cooled, densified, and slowly sank. By roughly 25 million years ago, most of it was below sea level. The only parts that remained exposed were the highest points of the original landmass: the southern Alps of New Zealand's South Island, the volcanic plateau of the North Island, and the raised coral limestone of New Caledonia. The implications were significant. Zealandia wasn't a sunken island or a submerged ridge. It was a full continental block that had undergone a process called tectonic thinning, the same process that pulls apart rift valleys but taken to its endpoint. The crust was still there. It had not been destroyed. It had simply dropped below the waterline. The rock record preserved in the exposed portions showed that Zealandia had once hosted terrestrial ecosystems: plant pollen, river deposits, coal seams. It had not always been ocean floor. Mapping of Zealandia's seafloor continues. In 2020, a marine survey by the research vessel RV Tangaroa revealed previously unknown ridges and basins within the submerged region. Rock samples recovered from these features confirmed their continental origin. The data suggested that Zealandia's submergence was not uniform. Some areas had subsided faster than others, creating a landscape of underwater plateaus and deep basins that may have been exposed as recently as 30 million years ago. The classification debate is largely settled. Zealandia appears on geological maps produced by New Zealand's government agencies. It is taught in university geology courses, but it does not appear on most political maps because no one lives on 94% of it. The continent exists. It simply doesn't look like one from above. Beneath the Pacific, the crust remains intact, still cooling, still thick enough to qualify as continental lithosphere. The water covering it is not a feature of the land, it is a condition of the elevation, and the elevation is still changing. Number 8. Kerguelen Plateau. A stretch of the southern Indian Ocean floor once hosted tropical forests, and the rock beneath them is still continental crust, not oceanic. Drilling operations by the Ocean Drilling Program in the late 1990s pulled up sediment cores from the Kerguelen Plateau, a raised expanse of seafloor roughly 2,300 kilometers long, located in the southern Indian Ocean, northwest of Antarctica. The cores contained pollen from tropical and subtropical plants, not cold-adapted species, warm climate flora that required mean annual temperatures above 15 degrees Celsius. The sediments were dated to the early Cretaceous, roughly 110 million years ago. The implication was direct. This part of the ocean floor had once been above water, and it had supported vegetation that could not have survived at its current latitude without significant changes in either climate or position. The plateau itself is not oceanic crust. That distinction is critical. Oceanic crust forms at mid-ocean ridges from basaltic magma and is relatively thin, typically 5 to 7 kilometers. Continental crust is thicker, less dense, and composed of a different suite of rocks: granites, gneisses. Sedimentary sequences. Seismic profiling of the Kerguelen Plateau revealed crustal thicknesses of 20 to 25 kilometers in some areas. The composition, sampled by drilling, included fragments of continental rock. This was not a volcanic ridge built on oceanic foundations. It was a fragment of continental lithosphere that had subsided below sea level. The Kerguelen Plateau formed as part of the Kerguelen Hotspot system, a mantle plume that generated enormous volumes of volcanic rock between 130 and 95 million years ago. At its peak, the plateau was a large island or archipelago, possibly connected to other elevated fragments in the region, including the Broken Ridge to the northeast. Sediment records indicate that it experienced multiple episodes of subaerial exposure, periods when the land surface stood above water long enough for soil formation and plant colonization to occur. One such episode lasted several million years. Charcoal fragments recovered in the cores suggest that wildfires occurred on the plateau, further confirming the presence of substantial vegetation and an oxygen-rich atmosphere at the surface. The cause of its submergence was thermal subsidence. When a mantle plume delivers magma to the surface, the overlying crust is heated and uplifted. Once the plume activity diminishes or the plate moves away from the hotspot, the crust cools. Cooling increases density. Increased density causes the crust to sink. This is not a catastrophic process. It is slow, continuous, and effectively irreversible on geological timescales. The Kerguelen Plateau sank over tens of millions of years. The last subaerial remnants, the Kerguelen Islands, home to a French research station, remain above water, but they are a fraction of what once existed. The plateau's significance lies in what it confirms. Continental crust can be produced by mantle plumes, and it can subside without being subducted. The Kerguelen Plateau did not collide with another plate. It was not forced into the mantle. It simply cooled and dropped. The process is still occurring. The plateau continues to subside at a rate measured in millimeters per century. The pollen found in those sediment cores is not a curiosity. It is a data point in a larger reconstruction. At some point in the Cretaceous, a landmass in the southern Indian Ocean was warm enough, high enough, and stable enough to support forests. That landmass is now between 1 and 2 kilometers below the surface. The forests are gone. The rock that supported them is not. And the sediments that buried them are still down there, layered in reverse order: forest floor on top of continental crust, ocean floor on top of the forest. Down to number 7. Argoland. A 3,000-mile landmass vanished 155 million years ago, and in 2023, geologists found it hadn't sunk. It had shattered into a ribbon stretching from Myanmar to the Andaman Sea. The breakup was not clean. When Argoland separated from the northwest margin of Australia during the late Jurassic, it did not drift away as a single coherent block. It disintegrated. The landmass, estimated at roughly 3,000 miles in length, fragmented into dozens of pieces, each carried in a slightly different direction by the tectonic forces pulling them apart. By the time the process ended, the pieces were scattered across a region now buried under the islands and shallow seas of Southeast Asia. For over a century, no one could account for where they went. The anomaly was first identified through plate reconstruction models. Geologists knew that a large section of continental crust had rifted away from the Australian plate approximately 155 million years ago. The margin where it detached, the Argo-Abyssal Plain, northwest of modern Australia, showed clear evidence of a separation event. Matching fracture zones, symmetrical magnetic anomalies, a well-defined spreading center. But the missing fragment, the piece that should have been on the other side, could not be located. Continents that break apart typically leave both halves visible. Australia had Gondwana's other fragments. Argoland had nothing. The question persisted for decades. Where did a 3,000-mile landmass go? In 2023, researchers at Utrecht University published a reconstruction that solved it. Argoland had not sunk. It had not been subducted. It had been shredded. By tracing tectonic units across Southeast Asia, mapping rock types, age signatures, and structural orientations, the team identified a chain of continental fragments extending from the Andaman Sea through the Mentawai Islands, southern Sumatra, western Borneo, and into the offshore regions of Myanmar. Each fragment shared a common geological fingerprint, the same age range, the same sedimentary sequence, the same paleomagnetic orientation. They were not separate terrains of different origins. They were pieces of a single landmass, torn apart and scattered across thousands of kilometers. The mechanism was extreme fragmentation driven by extensional tectonics. As Argolan pulled away from Australia, the crust behind it stretched, thinned, and broke. The resulting fragments were pulled into positions dictated by the rotation and movement of adjacent plates, the Indian plate to the west, the Eurasian plate to the north, the Pacific plate to the east. Some fragments were overridden by younger landmasses. Others were buried beneath volcanic deposits. A few were incorporated into the island arcs of present-day Indonesia. The pieces did not stay together. They were distributed like debris from a structural failure, each piece recording a slightly different vector of the same collapse. The discovery required a shift in how geologists think about continental breakup. The standard model assumes that when a continent rifts, it splits into 2 or 3 large fragments that drift apart. Argolan demonstrated that under certain conditions, a thin crust, rapid extension, a complex plate boundary geometry, a continent can be destroyed by dispersion. It does not sink. It does not collide. It simply ceases to exist as a continuous body, replaced by a field of fragments embedded in the crust of other plates. The result is a new category of continental loss. The fragments are still identifiable. Their rock signatures are still measurable, but reconstructing Argolan from its remains is not a matter of fitting 2 pieces together. It is a matter of reassembling a sheet of material that was torn into ribbons, scattered by currents, and buried under 150 million years of subsequent geology. The work is ongoing, and the full map of Argolan's fragments has not yet been completed. Number 6. Mauritius. Beach sand on Mauritius contains zircon crystals dated at 1.97 billion years, embedded in rock that formed only 9 million years ago. The zircon crystals were not supposed to be there. Beach sand collected from the island of Mauritius in 2013 yielded mineral grains dated at 1.97 billion years old. The island itself, a volcanic formation in the western Indian Ocean, roughly 2,000 kilometers off the southeast coast of Africa, is no older than 9 million years. The discrepancy is not a minor analytical error. It is nearly 2 billion years. Something ancient was buried beneath young rock, and the magma that built the island had carried fragments of that buried material to the surface during eruption. Mauritius sits atop the Mascairn Plateau, a submerged volcanic ridge positioned between Madagascar and the mid-Indian Ocean ridge. The island formed through repeated volcanic eruptions generated by a mantle plume, a column of abnormally hot rock rising from deep within the Earth's interior. Its surface geology is entirely basaltic, young, dark, dense, oceanic in character. No continental rock outcrops exist anywhere on the island. There are no granite formations, no sedimentary sequences, no metamorphic belts exposed at the surface. But zircon is a continental mineral. It crystallizes in granitic and metamorphic environments, not in the basaltic lava flows that constitute Mauritius. The grains found in the beach sand could not have formed locally. They had to originate from a fragment of much older continental crust, something buried below the volcanic pile, disrupted by the ascending plume, and expelled as xenoliths during eruption. That fragment was identified as Mauritius, a microcontinent that once occupied the ocean space between India and Madagascar during the late Cretaceous, roughly 85 to 60 million years ago. As the Indian Ocean widened and the Indian subcontinent drifted northward toward its eventual collision with Eurasia, the thin crust of Mauritius was subjected to intense extensional stress. It stretched, fractured into multiple segments, and gradually subsided below sea level. The fragments were left on the ocean floor, buried over tens of millions of years by younger volcanic rock and pelagic sediment. The zircon crystals recovered from Mauritius beach sand are physical evidence that one of those fragments lies directly beneath the island, intersected by the mantle plume conduit that later generated the volcanic eruptions building the land surface above. Subsequent studies reinforced the finding. In 2017, a separate research team recovered additional zircon grains from both beach sand and a rock core extracted from a drill hole on the island. The ages ranged from 1.97 billion to 660 million years, a spread consistent with a continental crustal fragment that had experienced multiple geological events across a vast timescale, not a single crystallization event. The drill core samples also revealed that the older material was not evenly distributed. It was concentrated in specific volcanic layers, indicating that the plume had intersected the continental fragment at depth and incorporated pieces of it into the ascending magma column during discrete eruptive phases. In 2020, new seismic refraction data revealed a zone of thickened crust, approximately 25 kilometers deep, beneath the Mascairn Plateau. That thickness is consistent with continental lithosphere, not the 5 to 7 kilometer thickness typical of oceanic crust in the surrounding region. The full extent of Mauritius remains unmapped. Gravity anomaly surveys suggest that additional fragments may lie scattered across the ocean floor between Mauritius and the Seychelles, a recognized continental fragment that is itself a remnant of the Gondwana breakup. Whether Mauritius was once physically connected to the Seychelles or existed as a separate microcontinental block is still unresolved. The reconstruction models differ. The data is incomplete. The fragments remain buried under volcanic rock and deep water, and the zircon crystals continue to appear in the sand, each grain a sample from a continent that no longer has a surface. Number 5. Mu, the Pacific Anomaly. The concept of a lost Pacific continent was dismissed for over a century, but modern seafloor surveys have revealed submerged plateau systems in the exact region where it was hypothesized to exist. The seafloor maps showed features that shouldn't have been there. In the central and western Pacific, modern bathymetric surveys revealed a series of elevated plateaus: the Ontong Java Plateau, the Maniki Plateau, the Hikurangi Plateau, rising thousands of meters above the surrounding ocean floor. These were not volcanic ridges in the conventional sense. They were enormous, flat-topped structures with crustal thicknesses that exceeded normal oceanic measurements. Some reached 30 to 35 kilometers thick. The standard model of Pacific geology had no clean explanation for structures of this scale and this geometry. The idea of a lost Pacific continent originated not with geologists but with antiquarians. In the 19th century, writers such as James Churchward proposed that a landmass called Mu had once spanned the Pacific, home to an advanced civilization before being destroyed by cataclysm. The claim was based on misreadings of Mayan and Sanskrit manuscripts, and it was dismissed by the scientific community as unsupported speculation. For decades, any suggestion of a lost Pacific landmass carried the stigma of pseudo-archaeology. The geology community treated the concept as a cautionary tale, an example of what happens when cultural mythology is mistaken for empirical observation. But the seafloor data complicated the dismissal. The plateaus identified in the Pacific, particularly Ontong Java, the largest oceanic plateau on Earth at roughly 1.9 million square kilometers, exhibited characteristics that partially matched continental crust. The rock samples recovered by drilling were predominantly basaltic, consistent with massive volcanic eruptions, but the scale of the eruptions was extraordinary. The Ontong Java Plateau alone represents an eruption volume of approximately 50 million cubic kilometers of magma, one of the largest volcanic events in Earth's history, occurring roughly 120 million years ago. The crust it produced was so thick that sections of it may have been subaerial, above water, for millions of years after formation. Sediment cores from the plateau contain evidence of shallow water environments. Some sections show signs of weathering consistent with exposure to air and sunlight. If the plateau's surface was above sea level for any significant period, it would have existed as an island or archipelago, a landmass in the Pacific, in roughly the same region where the Mu hypothesis had placed one. The coincidence is not confirmation, but it is not nothing either. The current scientific consensus holds that these plateaus are oceanic in origin, products of massive mantle plume eruptions, not fragments of pre-existing continental crust. They are classified as large igneous provinces, not continents, but the boundary between a very thick oceanic plateau and a very thin continental block is not always sharp. Some researchers have proposed that certain Pacific plateaus contain fragments of older continental material incorporated during the plume eruption process. The question remains open. The plateaus are now fully submerged. Thermal subsidence has pulled them below sea level over tens of millions of years. They are not rising. They are sinking. and the sediment layers on their surfaces continue to accumulate, burying whatever evidence might remain of their time above water. Number 4. Sunderland. During the last glacial maximum, Sumatra, Java, Borneo, and the Malay Peninsula formed one continuous landmass, larger than the European subcontinent. The sea level was 120 meters lower than it is today. That single fact redraws the map of Southeast Asia entirely. During the last glacial maximum, approximately 21,000 years ago, the shallow continental shelves connecting Sumatra, Java, Borneo, and the Malay Peninsula were fully exposed. The region was not an archipelago. It was a single, contiguous landmass called Sunderland, an extension of the Asian continental shelf that covered roughly 2.2 million square kilometers. It was larger than the European subcontinent. Sunderland was not a hypothetical construct. Its boundaries are defined by the 200-meter depth contour of the South China Sea, the Gulf of Thailand, the Java Sea, and the Strait of Malacca. When sea level dropped during the Pleistocene glaciations, these shallow marine areas became dry land. River systems crossed them. The paleo rivers of Sunderland, including the ancestors of the modern Mekong, Chao Phraya, and Sunda river systems, drained across the exposed shelf, creating a continuous lowland plain that linked what are now separate islands to the Asian mainland. The drainage patterns are still visible in the seafloor topography. Submerged river channels, some tens of kilometers wide, cut across the floor of the Java Sea and the South China Sea, tracing the paths water once followed when this region was land. The ecosystem was not uniform. The interior of Sunderland supported tropical rainforest, but paleoecological data indicates that drier, more open habitats existed in the central regions, where a rain shadow effect reduced precipitation. The margins supported mangrove swamps and estuarine wetlands. The biodiversity was enormous. Modern Sunderland, the fragmented, partially submerged version, is still one of the most biologically diverse regions on Earth. The pre-flooding version was significantly larger and more continuous, allowing species to disperse across the entire region without marine barriers. The submergence of Sunderland was not a single event. As the last glacial period ended, sea level rose in pulses, driven by meltwater inputs from the collapsing ice sheets of North America and Eurasia. The most rapid phase occurred between 14,000 and 7,000 years ago, when sea level rose at rates of up to 12 millimeters per year. The low-lying plains of Sunderland were progressively flooded. The Java Sea was inundated by roughly 10,000 years ago. The Strait of Malacca opened between 9,000 and 8,000 years ago, severing the last land connection between Sumatra and the Malay Peninsula. By approximately 6,000 years ago, Sunderland had been reduced to its present configuration, a mainland and a ring of islands, separated by shallow seas. The flooding displaced human populations. Archaeological sites in the region show evidence of settlement on the now submerged shelf. Stone tools and faunal remains have been recovered from the sea floor of the Java Sea and the Gulf of Thailand. These are not anomalies. They are remnants of a landscape that was occupied for tens of thousands of years before the water returned. The populations that lived on Sunderland were forced to retreat to higher ground, the areas that remain above water today. The modern distribution of ethnic and linguistic groups across Southeast Asia reflects, in part, the fragmentation of a population that was once continuous. The seas covering Sunderland are shallow. The sea floor is flat, sediment-covered, and in many places less than 50 meters deep. The shape of the lost landmass is not hidden. It is visible in the outlines of the continental shelf, and it is still vulnerable not to tectonic motion, but to the continued rise of global sea level. Number 3. Sahel. Australia, New Guinea, and Tasmania were joined by dry land for over 100,000 years, and the sea didn't separate them until just 8,000 years ago. The Torres Strait did not exist 12,000 years ago, nor did Bass Strait. Australia, New Guinea, and Tasmania formed a single continuous landmass called Sahel, a continent-scale entity separated from Sunderland to the west by a narrow but persistent marine gap, the Wallacean Corridor. The land bridge connecting the three components was not a thin strip of terrain. It was a broad plain, in places hundreds of kilometers wide, traversed by river systems and supporting a continuous terrestrial ecosystem. Sahel's existence as a unified landmass was a function of sea level. During glacial periods, when global ice volume increased and water was locked in continental ice sheets, sea level dropped sufficiently to expose the continental shelves connecting Australia to New Guinea across the Arafura Sea and the Gulf of Carpentaria, and to Tasmania across the Bass Strait. At maximum exposure, the combined area of Sahel exceeded 10.5 million square kilometers, roughly the size of Canada. The connection between Australia and New Guinea was particularly broad. The Sahel Shelf, which underlies the modern Arafura Sea and Torres Strait, is shallow, mostly less than 60 meters deep. A sea level drop of 120 meters, as occurred during the last glacial maximum, exposed this shelf entirely, creating a continuous lowland plain between the two landmasses. The separation happened late. The Bass Strait between Australia and Tasmania was inundated approximately 8,000 years ago, when rising seas breached the land bridge connecting the two. The Torres Strait between Australia and New Guinea flooded slightly earlier, around 9,000 to 8,500 years ago. These dates are remarkably recent in geological terms. For over 100,000 years, through the entirety of the last glacial cycle, Sahel existed as a single entity. Then, in a span of roughly 3,000 years, the water rose and the three components became islands. The biological consequences were significant. Sahel's flora and fauna evolved in isolation from the rest of the world, separated by ocean barriers from both Sundaland to the west and Antarctica to the south. The marsupial assemblages of Australia and New Guinea share common ancestry because they were part of the same continuous ecosystem during the glacial period. Tasmania's fauna was likewise connected. When the straits opened, populations were fragmented. Genetic divergence between Tasmanian and mainland Australian species, including the now extinct thylacine, accelerated after isolation. The separation was not just geographic, it was genetic, and it was irreversible. The human dimension is equally relevant. Sahel was the first continent settled by humans outside of Africa and Eurasia. Archaeological evidence places human arrival in Sahel at approximately 65,000 years ago, when sea levels were low, and the crossing from Sundaland required a sea voyage of no more than 90 kilometers. The populations that made this crossing dispersed across the entire Sahel landmass, from the arid interior of Australia to the highlands of New Guinea, while it was still a single continent. When the sea rose and the straits formed, those populations were permanently separated. The indigenous cultures of Australia, New Guinea, and Tasmania diverged in isolation for the next 8,000 years. The shelves that once connected them are still there. The Arafura Sea floor is flat, shallow, and geologically stable. The Bass Strait is slightly deeper but still well within the range of glacial sea level fluctuations. If another glacial period were to begin, on a timescale of tens of thousands of years, the land bridges would re-emerge. Sahel is not destroyed, it is submerged. Number 2. Beringia. A corridor 1,000 miles wide connected Siberia to Alaska for tens of thousands of years, and every indigenous population in the Americas may have walked across it. Land was exposed. For roughly 30,000 years, from approximately 45,000 to 15,000 years ago, a stretch of terrain connecting what is now Siberia to what is now Alaska stood above sea level. This was Beringia, a flat, cold, windswept plain spanning roughly 1,000 miles from north to south, sustained by a climate that was dry enough to prevent ice sheet formation, but cold enough to lock water in glaciers elsewhere on the planet. The sea level was 120 meters lower than today. The Bering Strait, now 85 kilometers of open water, did not exist. In its place was a continuous landmass, part of the continental shelf underlying the Bering Sea and the Chukchi Sea. Beringia was not a narrow bridge. It was a region. At its maximum extent, it covered approximately 1.6 million square kilometers, an area larger than Alaska itself. The terrain was not glaciated. Unlike the ice sheets covering much of northern North America, Beringia remained ice-free due to a combination of low precipitation and persistent high-pressure weather systems. The landscape supported a tundra steppe ecosystem. Grasses, sedges, dwarf willows, and a fauna that included mammoths, bison, saiga antelope, and lions. The productivity of this ecosystem was sufficient to support large herbivore populations, and by extension, the humans who hunted them. The archaeological record indicates that humans were present in Beringia by at least 25,000 years ago. Genetic evidence, particularly mitochondrial DNA and Y chromosome analyses of modern indigenous populations, supports a model in which a single founding population entered Beringia from Siberia and remained there, isolated, for several thousand years before expanding southward into the Americas. The Beringian standstill hypothesis proposes that this population diverged from its Siberian ancestors between 25,000 and 20,000 years ago, and that all indigenous populations in the Americas, from the Inuit of the Arctic to the Mapuche of southern Chile, descend from this isolated Beringian group. The flooding began around 15,000 years ago, as global temperatures rose and the ice sheets of the last glacial period began to collapse. Meltwater poured into the oceans. Sea level rose at rates exceeding 10 millimeters per year. The Bering Strait opened progressively, first as a narrow channel, then as a widening gap. By approximately 11,000 years ago, the land connection was severed. Beringia was submerged. The populations that had crossed it, or emerged from it, were cut off from Eurasia permanently. The seafloor of the Bering Strait is now between 30 and 50 meters deep. Below it lies the landscape those populations walked across. Sediment cores from the Bering Sea floor contain pollen records, plant macrofossils, and insect remains that confirm the tundra steppe ecosystem. Submerged beach ridges and river channels are visible in bathymetric data. The physical evidence of Beringia is intact, buried under shallow water, unexcavated over most of its area, and still capable of yielding information about the single most consequential human migration in the peopling of the Americas. Number 1. Kumari Kandam. The rift that separated Madagascar from India opened at roughly 2 centimeters per year, and the gap it created eventually drove India into Asia, building the Himalayas and reshaping global climate. India was moving north at 15 centimeters per year. No other tectonic plate on the modern Earth moves that fast, but between 80 and 40 million years ago, the Indian subcontinent, having separated from Madagascar and the broader Gondwana assemblage, surged northward across the Indian Ocean at rates that doubled or tripled the typical plate velocity. The force behind this acceleration is still debated. The leading hypothesis involves a combination of slab pull from the subducting Tethys ocean floor beneath southern Eurasia and a mantle plume pushing from below, thinning the Indian lithosphere and reducing resistance. Whatever the cause, the result was a continental collision of extraordinary scale. The collision occurred around 50 to 40 million years ago. India, a 4.5 million square kilometer continental block, struck the southern margin of Eurasia. The convergent boundary between them was already active. The Tethys Ocean had been subducting beneath Eurasia for tens of millions of years. But the arrival of continental crust, which cannot be easily subducted due to its low density, changed the dynamics entirely. The crust at the collision zone was compressed, folded, and thrust upward. The result was the Himalayan orogeny, a mountain-building event that produced the highest elevation range on Earth and continues to this day. But the chain of consequences did not stop at topography. The collision also reorganized oceanic circulation. Before India made contact with Eurasia, the Tethys Ocean provided an east-west seaway connecting the Atlantic to the Pacific at low latitudes. The collision closed this pathway. The closure forced global ocean currents to reorganize, contributing to the development of the modern thermohaline circulation system, the global conveyor that distributes heat across the planet. This reorganization is implicated in the global cooling trend that began around 50 million years ago and intensified toward the Pleistocene, ultimately driving the cycle of glaciations that included the very ice ages that exposed Sundaland, Sahel, and Beringia. The geological connection between Madagascar and India, the rift that started this entire sequence, opened roughly 88 million years ago. The separation occurred along what is now the central Indian Ocean basin, a region characterized by seafloor spreading ridges and fracture zones that record the divergence. Paleomagnetic data from both the Madagascar and Indian continental margins confirm that they were once contiguous. The rift opened at approximately 2 centimeters per year, slow by human perception, catastrophic by geological standards. As the gap widened, India was freed from its position within Gondwana and began its northward trajectory. Madagascar remained relatively stationary, anchored near its present position off the east coast of Africa. The concept of Kumari Kandam, a lost land connecting Madagascar to India, exists in Tamil literary tradition as a mythologized account of a sunken territory. The geological reality is that the connection did exist, not as a bridge but as a continuous continental configuration within Gondwana, and it was destroyed not by flood but by tectonic divergence. The process was slow, mechanical, and irreversible. The land did not sink, it was pulled apart. And the fragment that moved, India, went on to reshape the physical and climatic architecture of the entire planet. The Himalayas are still rising. India is still moving north, at roughly 5 centimeters per year. The collision zone generates earthquakes across a broad belt stretching from Iran to Myanmar. The Tibetan Plateau, elevated by the ongoing convergence, continues to influence atmospheric circulation patterns that control monsoon behavior across South and East Asia. The system set in motion by the separation of Madagascar and India 88 million years ago has not reached equilibrium. It is still running. The mountains are still growing. The climate is still responding. And the rift that opened between two fragments of Gondwana is still widening, millimeter by millimeter, on the floor of the Indian Ocean.